Hello everyone, I am Bireshwar Roy. I am pursuing my PhD in the Department of Physics, Indian Institute of Science, Bangalore, in the field of experimental condensed matter physics. In this video, I will be discussing the questions from the topic quantum mechanics came in the exam GATE Physics 2020. This question was asked in the GATE Physics paper 2020. This is a MCQ type question having 1 mark. The topic of the question is quantum mechanics. The question is, a quantum particle is subjected to the potential V as a function of x equals to infinity for x lesser equals to minus a by 2, equals to 0 for x greater than minus a by 2 but less than a by 2, and infinity for x greater than equals to a by 2. The ground state wave function of the particle is proportional to option A sin pi x by 2a, option B sin pi x by a, option C cos pi x by 2a, and the last option D cos pi x by a. Let us see how to solve this problem. The given potential profile according to the question is V as a function of x equals to infinity for x lesser equals to minus a by 2, equals to 0 for x greater than minus a by 2 but less than a by 2, and infinity x greater than equals to a by 2. The potential profile is shown by this schematic. Now we will consider the wave function for the particle in this given potential profile are psi 1x in the region 1, that is for x lesser equals to minus a by 2, psi 2 as a function of x in this region, that is x greater than minus a by 2 but less than a by 2, and in the third region the wave function is psi 3x, that is in the region x greater than equals to a by 2. Now the boundary conditions for this problem is given by psi 2 at x equals to minus a by 2 equals to psi 2 at x equals to a by 2 equals to 0. This is because in the first and third region the potential is infinity. So no particle wave function can exist in the infinite potential region. So psi 1x and psi 3x should be 0. Also at the boundary, these two wave function, that is psi 1 as a function of x and psi 3 as a function of x, should be 0. Now at the boundary also the wave function should be continuous. That is why the wave function psi 2 at the boundary, that is minus a by 2, and psi 2 at this boundary, that is at x equals to a by 2, should be 0. Now we will solve the one-dimensional Schrödinger equation in the region 2, that is in the region for x greater than minus a by 2 but less than a by 2, to get the particle wave function in this region. So the one-dimensional Schrödinger equation is given by minus h cut square by 2m times d square psi 2 as a function of x dx square plus v as a function of x times psi 2 as a function of x, where v as a function of x is the potential in that region, equals to E times psi 2 as a function of x, where E is the energy of the particle. Now in region 2 the potential is 0. So this equation can be written as d square psi 2 as a function of x dx square plus 2me by h cut square times psi 2x equals to 0. Now we will write this quantity 2me by h cut square as k square, where k is the wave vector for the particle wave function. So the equation can be written as d square psi 2x dx square plus k square psi 2x equals to 0, where k square equals to 2me by h car square. Now for our case, the energy of the particle is greater than 0, that is E greater than 0. It concludes that k square should be greater than 0. So k has the real value. For this kind of condition, the solution of the equation will be psi 2 as a function of x equals to a times sin kx plus b times cos kx. Here a and b are the constants. Now we will apply the boundary conditions, that is psi 2 at x equals to minus a by 2 equals to psi 2 at x equals to a by 2 equals to 0. Now we found that our wave function in the region 2, that is psi 2 as a function of x equals to a times sin kx plus b times cos kx. At x equals to minus a by 2, the psi 2x is minus a sin k by 2 plus b cos k by 2, that is equal to 0. It is coming from this boundary condition. Also, psi 2 at x equals to a by 2 equals to a times sin k by 2 plus b times cos k by 2 equals to 0. So we have these two equations now. First, we'll add up these two equations. So we'll get psi 2 at x equals to minus a by 2 plus psi 2 at x equals to a by 2 equals to 2b times cos k by 2 equals to 0. So we have cos k by 2 equals to 0. Now any cosine function can be 0 for the values k by 2 equals to any odd multiple of pi by 2. So our k by 2 will be odd multiple of pi by 2. So that can be written as 2n plus 1 times pi by 2, where n takes the values 1, 2, 3 and so on. So integer values will be taken by n. We can write this as k by 2 equals to m pi by 2, where m equals to 2n plus 1. So the values for m will be odd integer values, that is 1, 3, 5 and so on. So we found that our k value will be m pi by a, where m equals to odd integers, that is 1, 3, 5 and so on. And at this condition, the a equals to 0 and b not equals to 0. So we can write the wave function psi 2 as a function of x equals to b with a subscript m times cos m pi x by a, where m equals to odd integer values. Similarly, we will subtract those two equations, that is psi 2 at x equals to a by 2 minus psi 2 at x equals to minus a by 2 equals to 2a times sin k by 2 equals to 0. So from here we can write sin k by 2 equals to 0. That means k by 2 will be integer multiple of pi. So n will be 1, 2, 3 and so on. We can write this k as 2n times pi by a. Now we will write this 2n as m. So m will take the values 2, 4, 6 and so on. So the m values will be even integers. So we have k equals to m pi by a, where m takes the even integer values, that is 2, 4, 6 and so on. And for this condition, the a not equals to 0 but b equals to 0. So the particle wave function will be psi 2 as a function of x equals to a with subscript m times sin m pi x by a for m equals to even integer values. So the complete solution for the particle wave function will be psi 2 as a function of x equals to am times cos m pi x by a for m equals to odd integer values, and psi2 as a function of x will be bm times sin m pi x by a for m even integer values. Now for the ground state, m value will be 1, that is odd. The particle wave function at the ground state will be psi2 as a function of x equals to a1 times cos pi x by a. So the particle wave function will be proportional to cos pi x by a. Hence, the ground state wave function, that is for m equals to 1, of the particle is proportional to cos pi x by a. That is our option D. Now, we will see a different approach to solve this problem. We can solve this problem with the help of a known result. Let us consider this kind of potential profile. That is, the potential is infinite for x lesser equals to 0. The potential is 0 for x greater than 0 but x less than a, and the potential is infinite for x greater than equals to a. So this is a very well-known problem for a particle in a potential well having width a. For this problem, we know the solution will be psi1x and psi3x will be 0 in the infinite potential regime, and psi2x will be root over 2 by a times sin n pi x by a, where n takes the integer values, that is 1, 2, 3 and so on. So using this solution, we can get the solution for the given problem. Now we will shift the origin from x equals to 0 to x equals to a by 2 in the older well-known potential problem. So if we shift our origin from x equals to 0 to x equals to a by 2 in this potential profile, so our coordinate system will get transformed. So in the new coordinate system, the potential profile will look like this. So the potential barriers in the transform coordinate will be at x dash equals to minus a by 2 and at x dash equals to a by 2. So now we get the potential profile same as the given in the question. In the new coordinate system, after transformation, we can connect the older coordinate system to our new coordinate system, and that is given by x dash equals to x minus a by 2. So we can write x equals to x dash plus a by 2. So the particle wave function in the new coordinate system will be transformed from psi2 as a function of x, that is the older wave function in the well-known potential problem, to psi2 as a function of x dash in the new or transformed coordinate system. Now for the older problem, we know psi2 as a function of x is equal to root over 2 by a times sin n pi x by a. Now we have transformed our coordinate system from x to x dash. So psi2 as a function of x dash will be root over 2 by a times sin n pi by a times x dash plus a by 2, because x has transformed to x dash plus a by 2. That has been shown in the previous slide. So the wave function in the transfer coordinate system will be root over 2 by a times sin n pi by 2 plus n pi x dash by a. For ground state, that is for n equals to 1, we have psi2 x dash equals to root over 2 by a times sin pi by 2 plus pi x dash by a. So this will give us root over 2 by a times cos pi x dash by a. Hence, the ground state wave function of the particle is proportional to cos pi x by a. That is the option D given in the question. We solved this problem in two different ways. From both the solutions, we found that the answer for this question, that is the ground state wave function of the particle, is proportional to option D, that is cos pi x by a. This question is from the GATE Physics paper 2020. This is a MCQ type question having 1 mark. The topic of the question is quantum mechanics. The chapter is harmonic oscillator. The question is, let a cap and a cap dagger respectively denote the lowering and raising operators of a one-dimensional simple harmonic oscillator. Let the state n be the energy eigenstate of the simple harmonic oscillator, given that the state n is also an eigenstate of a cap dagger times a cap dagger times a cap times a cap. The corresponding eigenvalue is option A, n into n minus 1, option B, n into n plus 1, option C, n plus 1 whole square, and the last option, option D, n square. Let us see how to solve this problem. Before going to the solution part of this problem, let us recapitulate briefly about the operator methods used in the harmonic oscillator problem and the properties of the operators. We know the Hamiltonian for the simple harmonic oscillator has the form H cap, that is the Hamiltonian operator, equals to P cap square divided by 2m plus half m omega square x cap square. Here P cap is the momentum operator, m is the particle in the harmonic oscillator potential, omega is the angular frequency of the harmonic oscillator, and x cap is the position operator. Now we know the commutation relation between the position operator x cap and the momentum operator p cap equals to I h cut. Here I is the root over minus 1 and h cut is the reduced Planck's constant. Now we define two special type of operators. Those are a cap dagger and a cap. A cap dagger is defined as root over m omega divided by 2h cut times x cap operator minus I times p cap operator divided by root over 2m omega h cut. And the second operator a cap is defined as root over m omega divided by 2h cut times x cap operator plus I times the p cap operator divided by 2m omega h cut. It is clearly seen that these two operators a cap and a cap dagger are complex conjugate of each other. The a cap dagger operator is known as creation or raising operator, and the operator a cap is known as annihilation or lowering operator. There is some importance or significance of the nomenclatures for these two operators a cap and a cap dagger. When the operator a cap dagger acts on a harmonic oscillator state n, it returns the state n plus 1. Basically, it is raising the state by 1. That is why it is known as creation or raising operator. Similarly, when the operator a cap acts on a harmonic oscillator state n, it returns the state n minus 1. So basically it annihilates or lowered the state by 1. That's why the name of this operator is annihilation or lowering operator. Now we'll evaluate the quantity a cap dagger times a cap. So we'll take the multiplication of these two terms which are coming from the expressions of the a cap dagger and a cap. After multiplication, it will give 4 terms. Those are m omega divided by 2h cut times x cap square plus I x cap p cap divided by 2h cut minus I p cap x cap divided by 2h cut plus p cap square divided by 2m omega h cut. Now we'll rearrange the terms. So we'll take the first term and the fourth term together, and it will give 1 by h cut omega times p cap square divided by 2m plus half m omega squared x cap square. And we'll take the second and third term together. It will give I by 2 h cut times x cap p cap minus p cap x cap, which will give the commutator bracket of x cap and p cap. Now if we see carefully, the terms in the parentheses are basically giving the Hamiltonian for our harmonic oscillator problem. So we can write it as h cap, that is the Hamiltonian operator, divided by h cut omega plus I by 2 h cut times I h cut. Here I h cut is coming due to the commutation relation between the x cap and p cap operator. So the a cap dagger a cap equals to h cap divided by h cut omega plus I by 2 h cut times I h cut. So from the numerator and denominator, h cut will be cancelled out, and the multiplication of I and I will give -1. So we can write a cap dagger times a cap equals to h cap divided by h cut omega minus half. From here, we'll get an expression for the Hamiltonian operator, that is h cap, equals to a cap dagger times a cap plus half, these terms in the parenthesis, times h cut omega. Now let us see some commutation relations related to the operators a cap dagger, and the Hamiltonian operator h cap. Those are the commutation relation between a cap and a cap dagger operator equals to 1. The commutation relation between the h cap and a cap operators is equal to minus h cut omega a cap operator, and the commutator of the h cap and a cap dagger operator is h cap omega times a cap dagger. Here the a cap dagger a cap is known as number operator n cap, because when this operator a cap dagger a cap or the operator n cap operates on a harmonic oscillator state n, it returns the eigenvalue n, that is the value of the state of the harmonic oscillator. Here the state n is basically nth eigenstate of the harmonic oscillator. Now according to the question, we have to deal with the operator O cap equals to a cap dagger, a cap dagger, a cap and a cap. And it is also given the state n is the eigenstate of the O cap operator. So we can write O cap operates on the state n equals to some eigenvalue lambda times the state n. So in the question, we have to find the value of lambda. So our O cap operator is a cap dagger, a cap dagger, a cap and a cap. Now we'll take the second and third operators, those are a cap dagger and a cap together, and using the commutation relation between the a cap and a cap dagger operator, we can write these a cap dagger a cap equals to a cap dagger minus 1. So we have O cap operator equals to a cap dagger times a cap dagger minus 1 times a cap. Now first we will multiply this a cap dagger with the terms in the parenthesis. So we'll get a cap dagger times a cap dagger minus a cap dagger times a cap. Then we can multiply this a cap from the right hand side. So we'll get a cap dagger a cap times a cap dagger a cap minus a cap dagger a cap. So we have taken this ACAP dagger ACAP in the parenthesis in each case. Now we can identify this ACAP dagger ACAP is basically our number operator, that is the incap operator. So we'll write this as incap times incap minus incap. So basically our OCAP operator in terms of the number operator is incap square minus incap. The operator OCAP is acting on the state in. Now OCAP operator is incap square minus incap operator. So we can write the incap square operator minus incap operating on the state in. It will give incap square operating on the state in minus incap operating on the state in. Now the eigenvalue for this incap square operator is n square and the eigenvalue for the operator incap is n. So we can write it as n square minus n times the state n. So we can see the eigenvalue for the operator OCAP is n into n minus 1. According to the solution, we found that when the operator ACAP dagger, ACAP dagger, ACAP, ACAP is acting on the eigenstate n, it returns the eigenvalue, the option A, that is n into n minus 1. So option A is the correct answer for this question. This question was asked in the GATE Physics paper 2020. This is a MCQ type question having 1 mark. This question is from the topic quantum statistics. The question is, choose the correct statement related to the Fermi energy EF and the chemical potential mu of a metal. Option A is mu equals to EF only at 0 Kelvin. Option B, mu equals to EF at finite temperature. Option C, mu less than EF at 0 Kelvin. And the last option, option D, mu greater than EF at finite temperature. Let us see how to solve this problem. We know the Fermi-Dirac distribution function in discrete form is given by the average number or the occupation number of the particles at the energy level EA is 1 by 1 plus exponential of EA minus mu by kBT, where mu is the chemical potential. Now, if we want to see the plot of this function, then we'll get two nature of this function, that is at t equals to 0, it will be a step function. So this function will have value 1 less than the energy EF equals to mu, and at t greater than 0 Kelvin it will be a decreasing function like this, and at mu it will have 50% occupation probability, that is it will have a value half. Now let us choose a temperature very close to 0 Kelvin. So at this temperature, this exponential term, that is exponential of EA minus mu by kBT, will tend to infinity plus infinity if our energy EA is greater than mu, and this exponential term will be very small positive value close to 0 if our energy level is less than our chemical potential mu. So the average number of the particle, that is the occupation number, will be 1 if EA is less than mu, and it will be 0 if EA is greater than mu when the temperature is very close to 0 Kelvin. So from here we can conclude that we get that at t equals to 0 Kelvin, that is absolute 0, the Fermi energy level is equal to chemical potential energy, that is EF equals to mu at t is equal to 0 Kelvin. So our option A is correct in this case. So for this question, the first option, option A, that is mu equals to EF only at 0 Kelvin, is the correct option. This question was asked in the GATE Physics paper 2020. This is a MCQ having 2 marks.
The topic of the question is quantum mechanics. The question is, the operator Sx cap denotes the spin operator defined as Sx cap equals to h cut by 2 times the matrix 0, 1, 1, 0. Which one of the following is correct? There are four options given. Option A, the eigenstates of spin operator Sx cap are up spin equals to 1, 0 matrix and down spin equals to 0, 1 matrix. Option B, the eigenstates of the spin operator Sx cap are up spin equals to 1 by root 2 matrix 1 minus 1, and this will be down spin. Down spin is equals to 1 by root 2 times the matrix 1, 1. Option C, in the spin state 1 by 2 times the matrix 1 root 3. Upon the measurement of Sx cap, the probability for obtaining up spin is 1 by 4. And the last option, option D, in the spin state 1 by 2 times the matrix 1 root 3. Upon the measurement of Sx cap, the probability for obtaining the up spin is 2 plus root 3 divided by 4. So among the four options, we have to choose the correct one. Let us see how to solve this problem.
So it is given in the question that the spin operator, that is the x component of spin, Sx cap equals to h cut by 2 times this matrix 0, 1, 1, 0. Now this matrix 0, 1, 1, 0 can be written as sigma x, which is one of the Pauli matrix. So Sx cap equals to h cut by 2 times this Pauli matrix sigma x. Now we have to find what are the eigenvalues and eigenvectors for the spin operator Sx cap. So essentially we will find the eigenvalues for sigma x. Then we can easily find the eigenvalues for Sx cap operator. So essentially we will find the eigenvalues for sigma x, then we will multiply h cut by 2 with the eigenvalues of the sigma x or the Pauli matrix. So for that, what we have to do, we have to calculate this determinant, that is sigma x minus lambda times I2. So here lambda is the eigenvalue of the Pauli matrix sigma x and I2 is the 2 cross 2 unit matrix, and this determinant should be equal to 0. So if we write this whole thing in the matrix form, then it will become determinant of this matrix 0, 1, 1, 0, that is the sigma x matrix, minus lambda times the I2 matrix, that is 1, 0, 0, 1, that is equals to 0. So it will basically give determinant of minus lambda 1, 1 minus lambda equals to 0. So we'll get lambda squared minus 1 equals to 0. So lambda equals to plus minus 1. Hence the eigenvalues for the Pauli matrix sigma x are plus minus 1. So we'll denote lambda plus equals to plus 1 and lambda minus equals to minus 1. These are the two eigenvalues for sigma x. So the eigenvalues for this operator Sx cap will be basically h cut by 2 times lambda plus and h cut by 2 times lambda minus. So the eigenvalues of this spin operator Sx cap are plus minus h cut by 2. Now we'll find the eigenstates for this spin operator Sx cap. Let us consider uv represents the eigenstate of Sx cap. So it is also known as spinor. To find the eigenstates, what we will do, we will consider this Sx operator times the eigenstate uv equals to the eigenvalue, that is plus minus h cut by 2 times the spinor or the eigenstate uv. Now Sx cap is basically h cut by 2 times the Pauli matrix sigma x. So from both sides we can cut the h cut by 2, and sigma x is 0, 1, 1, 0. Then we can multiply this 0, 1, 1, 0 matrix with the column matrix uv, and that is equals to plus minus uv matrix. So it will give vu matrix equals to plus minus uv matrix. So we will get v equals to plus minus u. For the eigenvalue plus h cut by 2, we will have v equals to u. For the eigenvalue minus h cut by 2, we will have v equals to minus u. Let us choose u equals to 1. Then v equals to 1 for the eigenvalue plus h cut by 2 and v equals to minus 1 from this equation for eigenvalue minus h cut by 2. So eigenvectors or eigenstates for the spin operator Sx cap will be 1 1 and 1 minus 1, but they are not normalized. So in the normalized form, the eigenvectors or the eigenstates for the spin operator Sx cap will be up spin, that is 1 by root 2 times the column matrix 1 1, and the down spin, that is the 1 by root 2 times 1 minus 1 matrix. Now, if any spin state, that is the state or kth of phi, is given, upon the measurement of the spin operator Sx cap, the probability for obtaining the up spin state or down spin state of the x component is mod square of the inner product between up spin and phi state, or mod square of inner product between down spin and phi state. Now, let us check the options given one by one. So, option A, that is given the eigenstates of the spin operator Sx cap are up spin, that is 1 0, and down spin, that is 0 1. So this is false because we have already calculated the eigenstates or eigenvectors for the Sx cap operator is 1 by root 2 times the column matrix 1 1, and for down spin, that is 1 by root 2 times the column matrix 1 minus 1. So this option is false. Now option B is given the eigenstates of this spin operator Sx cap are for up spin, that is 1 by root 2 times the column matrix 1 minus 1, and for the down spin 1 by root 2 times the column matrix 1 1. So this is also false because for up spin it will be 1 by root 2 times the matrix 1 1, and for down spin it will be 1 by root 2 times the column matrix 1 minus 1. So option B is false in this case. Now option C, it is given that in the spin state 1 by 2 times the column matrix 1 root 3, upon the measurement of Sx cap, the probability for obtaining up spin is 1/4. So in our case, the given state phi is 1 by 2 times the matrix 1 root 3, and up spin state, that is 1 by root 2 times the column matrix 1 1, that we have calculated in the previous slide. Now in the spin state 1 by 2 times the column matrix 1 root 3, upon the measurement of Sx cap operator, the probability for obtaining up spin state is given by P equals to mod square of inner product between the up spin state and the phi state, that is 1 by 2 times matrix 1 root 3. So this bra of up spin will give this row matrix, that is 1 by root 2 times the row matrix 1 1, and the state of phi state, that will be 1 by 2 times the column matrix 1 by 1 root 3, and we have to take mod square of this. So we can take out this 1 by 2 and 1 by root 2 from this mod square. So it will give 1 by 2 root 2 whole square times mod of the multiplication between these two matrix 1 1 and 1 root 3 and mod of this square. So this will give 1 plus root 3 mod square whole square, and this will give 1 by 8. So we'll get effectively 1 plus 3 plus 2 root 3. So this is the 1 plus root 3 whole square divided by 8. So it will give 4 plus 2 root 3 divided by 8, and after simplification it will give 2 plus root 3 divided by 4. So it is not matching with our option C. So option C is false in our case. Now option D is saying in the spin state 1 by 2 times the column matrix 1 root 3, upon the measurement of Sx cap, the probability for obtaining up spin state is 2 plus root 3 by 4. So this is true because we have already calculated this probability in the option C, And from the option C, we have found that the probability will be 2 plus root 3 divided by 4. So the option D is correct in our case.
So according to our solution, the last option, option D, that is in the spin state 1 by 2 times matrix 1 root 3, upon the measurement of a six-cap operator, the probability for obtaining the upspin is 2 plus root 3 divided by 4. So this is the correct one for this question. This question is from the GATE Physics paper 2020. This is a numerical answer type question having 2 marks, and the topic of the question is quantum mechanics. The question is, the radial wave function of a particle in a central potential is given by r as a function of small r, that is position, equals to a times small r by a times exponential of minus small r divided by 2a, where a is the normalization constant and small a is positive constant of suitable dimensions. If gamma a is the most probable distance of the particle from the force center, the value of gamma is, so we have to find the value of gamma so that the gamma a is the most probable distance of the particle from the force center in this question. Let us see how to solve this problem. According to the question, the radial wave function is given by r as a function of position small r equals to a times r divided by a times exponential of minus r by 2a. Therefore, the probability of finding the particle between r and r plus dr is given by p as a function of r times dr equals to 4 pi r square times mod of capital R as a function of smaller mod square equals to 4 pi a square divided by a square times r to the power 4 times exponential of minus r by a times dr. Here a is the normalization constant and a is the positive constant of suitable dimensions. To find the most probable distance r of the particle from the force center, or the value of r where the probability of finding the particle is maximum, we can say in this case the derivative of the probability density function Pr with respect to the position r should be 0. So this will give ddr of 4 pi a square divided by small square times r to the power 4 times exponential of r minus r by a equals to 0. So if we do the derivatives, so we'll get 4r cube times exponential of minus r by a plus r to the power 4 times minus 1 by a times exponential of minus r by a, that is equal to 0. So we can do the little rearrangement here. So we'll get 4 minus r by a times r cube times exponential of minus r by a equals to 0. Therefore, we can say 4 minus r by a equals to 0, since the other terms with it, that is r cube times exponential minus r by a, that cannot be 0 here. So from here we will get r equals to 4a, given the most probable distance is gamma a. So if we compare this with 4a, then we'll get gamma value is 4. So if gamma a is the most probable distance of the particle from the force center, then the value of gamma will be 4. Now we will discuss some important tricks to solve this kind of problem. So the radial function given in the question is similar to the radial part of the hydrogen atom wave function. For the hydrogen atom problem, if the radial part of the hydrogen atom is proportional to exponential of minus r divided by Na. Therefore, the principal quantum number in that case will be n. And for the principal quantum number n, the probability of finding the particle or electron in the hydrogen problem is maximum at r equals to n square a. So if we use this relation, so in the given question, it is the n value is 2. So the most probable distance will be r equals to 2 square a, that is 4a. So our gamma value will be 4 in that case. So we have solved this problem, and also we have discussed some important tricks to solve this type of problem very easily. And we found that the gamma value in this question is 4. This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 2 marks, and this question was asked from the topic quantum mechanics. The question is, a free particle of mass capital M is located in a 3-dimensional cubic potential well with impenetrable walls. The degeneracy of the fifth excited state of the particle is, so we have to find the degeneracy of the fifth excited state of this particle in this cubic potential well. Let us see how to solve this problem. We know the energy spectrum of the 3-dimensional cubic potential well of site capital L is E nx ny nz equals to pi square h cut square divided by 2 capital M capital L square times nx square plus ny square plus nz square. Here h cut is the reduced Planck constant. Capital M is the mass of the particle in this 3-dimensional cubic potential well, and L is the side of the well, and nx, ny and nz denote the 3 quantum numbers for this problem. So we can write this as alpha times p, where p is this sum, that is nx square plus ny square plus nz square, and alpha is this constant term, that is pi square h cut square divided by 2m capital L square. Here nx, ny and nz, all of these quantum numbers can take the integer values, that is 1, 2, 3, 4 and so on. Let us see the energy configuration for a free particle in 3-dimensional cubic potential well with impenetrable walls. We'll see it in the next slide. Now, let us see the possible energy configurations for the quantum numbers nx, ny, nz and their corresponding energies and degeneracy. So, for the ground state, nx, ny and nz, all of them will be 1. So, for the set 1, 1, 1, the p value is 3. Here p is the nx square plus ny square plus nz square. And the corresponding energy value in the ground state is E1 equals to 3 alpha. So here only one possible set is there in the ground state, so degeneracy will be 1. In the first excited state or the second state, the nx can take value 2, ny can take value 1 and nz can take value 1. Or alternatively, the other possible sets are 1, 2, 1 and 1, 1, 2. So there are 3 possible sets in the first excited state. The p value will be 6 for all of the states, and the energy value E2 will be 6 alpha. And clearly their degeneracy is 3 in the first excited state. Similarly, for the second excited state, the possible sets for the nx, ny, nz are 2, 2, 1, 2, 1, 2 and 1, 2, 2. The p value will be 9 here, and the energy value for this second excited state E3 is 9 alpha. So the degeneracy here is 3. For the third excited state, The possible sets for the quantum numbers nx, ny and nz are 113, 131 and 311. So three possible sets are there. The p-value is 11 and the energy value for this third excited state E4 equals to 11 alpha, and clearly the degeneracy is 3 in this third excited state. For the fourth excited state, only one possible set is there, that is 222. The p-value is 12 here, and the energy value for the fourth excited state E5 equals to 12 alpha. So the degeneracy is 1 in this state. And the fifth excited state will have the possible quantum number sets, that is 123, 213, 231, 132, 312 and 321. So all the 6 states will lie in the fifth excited state, and the p-value is 14. The corresponding energy value for this fifth excited state is E6 equals to 14 alpha. So the degeneracy in the fifth excited state is 6. The fifth excited state of the particle has the energy E6 equals to 14 alpha, that is actually 14 times pi squared h car squared divided by 2m L square. The possible sets of quantum numbers that we have seen in the previous slide, nx, ny, nz are 123, 213, 231, 132, 312 and 321. So there are 6 possible sets. So the degeneracy of the fifth excited state of the particle is 6 here. We have discussed the solution for this question very thoroughly, and we found that the degeneracy of the fifth excited state of the particle in this cubic potential well is 6.
This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 2 marks, and the topic of the question is quantum mechanics. The question is, an electron in an hydrogen atom is in the state n equals to 3, L equals to 2 and m equals to -2. Let Ly cap denote the y component of the orbital angular momentum operator. If del L Ly cap whole square equals to alpha h car square, then the value of alpha is, so we have to find the value of alpha in this equation. Let us see how to solve this problem. So before going to the main solution part, we will be discussing some mathematical formulation of operators which will be useful in our solution part. So let us discuss this first. The state of the electron in the hydrogen atom is L, ml. So basically this state is orbital angular momentum state. Now we define the raising operator as L plus cap equals to Lx cap plus IL cap, and lowering operator is L minus cap equals to Lx cap minus IL cap. In terms of this raising operator and lowering operator, we can represent our Lx cap and Ly cap. So Lx cap will be L plus cap plus L minus cap divided by 2. Ly cap is L plus cap minus L minus cap divided by 2y. So it will be I by 2 times L minus cap minus L plus cap. Now when this L plus cap operator acts on this state L comma ml, it will give the value root over L minus ml times L plus ml plus 1, and with this state L comma ml plus 1. So basically this operator L plus acting on this state L comma ml will raise the value ml by 1. That's why it is called raising operator. And when L minus cap operator will act on the state L comma ml, it will give root over L plus ml times L minus ml plus 1 times this state L comma ml minus 1. So basically this operator L minus acting on the state L comma ml is lowering the value of ml by 1. That is why it is known as lowering operator. Now let us see what is the value of this element, that is L plus cap operator is sandwiched between state L comma ml dash and L comma ml. So L plus cap operator will act on this state L comma ml and it will give this value h cut times root over L minus ml times L plus ml plus 1, and it will give a inner product between L comma ml dash and L comma ml. So as all the L and ml states are orthogonal, so the inner product will give delta of ml dash comma ml plus 1. So this value will be 1 when ml dash equals to ml plus 1, and it will be 0 when ml dash is not equals to ml plus 1. Similarly, this matrix element, that is L minus cap operator sandwiched between these two states L comma ml dash and L comma ml, it will give h cut times root over L plus ml times L minus ml plus 1 times this delta function ml dash comma ml minus 1. Now this matrix element value, that is L plus cap operator whole square sandwiched between these two state L comma ml dash and L comma ml, it will give h cut times root over L minus ml times L plus ml plus 1. So basically it is coming when we are acting this L plus operator on this L comma ml state. So remaining term will be L comma ml dash state, and L plus cap is sandwiched between these two state, that is L comma ml dash and L comma ml plus 1. So this state is already raised by 1 because of this operation L plus 1 by 1 time. So after this operation we will get h cut square times L minus ml times L plus ml plus 1 times L minus ml minus 1 times L plus ml plus 2 to the power half, and it is multiplied with this delta function, that is delta ml dash comma ml plus 2. So it will be non-zero when ml dash equals to ml plus 2. Similarly, we can find this matrix element, that is L comma ml dash and L comma ml, where L minus operator square is sandwiched between these two state. So it will give h cut square time L plus ml times L minus ml plus 1 times L plus ml minus 1 times L minus ml plus 2 whole to the power half times this delta function, that is delta of ml dash comma ml minus 2. So it will be non-zero when ml dash equals to ml minus 2. Now we have to find this quantity, that is del ly cap whole square. So this means basically expectation value of ly cap square minus expectation value of ly cap whole square. Now we will find this expectation value of ly cap. So this means ly cap is sandwiched between this same state, that is L comma ml. Now we can represent this ly cap as I by 2 times L minus cap minus L plus cap in terms of the raising and lowering operator that we have seen in the earlier slides. So we are getting I by 2 times this element, that is L minus cap sandwiched between this LML state, and that is expectation value of L minus operator. Similarly, minus expectation of L plus cap operator. Now L minus state operating on this state LML, it is lower the state and it will give a state L comma ml minus 1 with some prefactor. But because of the orthogonality, the LML state inner product with L comma ml plus ml minus 1, it will give 0. Similarly, for this case also we will get 0. So it will be I by 2 times 0 minus 0. So essentially the expectation value of the ly cap operator will be 0. Now ly cap square, this operator can be written as I by 2 times L minus cap minus L plus cap times the same thing, that is I by 2 times L minus cap minus L plus cap.
So after multiplication we will get minus 1 by 4 times L minus square minus L minus L plus minus L plus L minus plus L plus square. Now the L plus times L minus operator equals to Lx cap plus ILy cap minus Lx cap minus ILy cap. So basically we are writing this L plus and N minus in terms of Lx and Ly. So after multiplication we are getting Lx square plus Ly square minus iota times this commutation of Lx cap comma Ly cap. Now this commutation value is iota h cut Lz. So we can write L plus L minus operator is equals to L square minus Lz square plus h cut Lz. Similarly, we can find this thing L minus L plus equals to L square minus Lz square minus h cut Lz. So essentially after putting this thing in the main expression of Ly square, that is minus 1 by 4 times L minus square plus L plus square minus of this L minus L plus, that is L square minus Lz square minus h cut Lz minus L plus L minus, that is L square minus Lz square plus h cut Lz. So after doing all calculations we are getting Ly square equals to minus 1 by 4 times L minus square plus L plus square minus 2L square plus 2Lz square. So basically Ly square equals to half of L square minus half of Lz square minus 1 by 4 L plus square minus 1 by 4 L minus square. So we need this to find the expectation value of Ly square. So we have Ly square equals to half of L square minus half of Lz square minus 1 by 4 L plus square minus 1 by 4 L minus square. So the expectation value of Ly squared is this. So we'll use the expression for Ly square here. So we'll get 4 terms because there are 4 terms in the Ly square in this expression. So we'll get half of expectation value of L square minus half of expectation value of Lz square minus 1 by 4 of expectation value of L plus square minus 1 by 4 expectation value of L minus square. Now we have seen this expectation value will be non-zero when this ml value is basically 2 times greater than this ml. So but here it is same, so it will give 0. By the same reason this element will also be 0. So effectively these two terms will be 0, but these two terms, first two terms will survive, and expectation value of L square is L into L plus 1 times h cut square, and expectation value of Lz square is basically m h cut whole square. So we'll get half of L into L plus 1 times h cut square minus half of ml h cut whole square, and other two terms will give 0. So what we have, the expectation value of Ly square equals to h cut square times L into L plus 1 minus ml square. So this quantity, that is del of Ly cap whole square, is basically expectation value of Ly square minus expectation value of Ly whole square. So this expectation value Ly is 0, so the surviving term will be expectation value of Ly square. This will give h cut square by 2 times L into L plus 1 minus ml square. So our del of Ly cap whole square is basically h cut square times L into L plus 1 minus ml square. So this is the expression for general state L comma ml. Now it is given in the question n equals to 3, L equals to 2 and ml equals to minus 2. So we need these values L and ml. We'll put this in this equation. So we'll get del of Ly whole square equals to h cut square by 2 times 2 into 2 plus 1 minus 2 whole square. So it will give h cut square by 2 times 6 minus 4, and we'll essentially get h cut square. Now it is given in the question, that is del L y cap whole square is equals to alpha h cut square. Here alpha equals to 1 from our result. So the final result is alpha equals to 1. So according to our solution for this electronic state in the hydrogen atom, that is n equals to 3, L equals to 2 and m equals to minus 2, the value of this del L y cap whole square equals to h car square. So the alpha value will be 1 in our case.
This question was asked in the GATE Physics paper 2020. There is a numerical answer type question having 2 marks, and the topic of the question is quantum mechanics. The question is, consider the Hamiltonian h cap that is divided into two parts equals to h naught cap plus h dash cap, where h naught cap is 3 cross 3 matrix, that is E00, 0E0, 00E. So it is a diagonal matrix. And h dash cap is the time independent perturbation given by h dash cap equals to this 3 cross 3 matrix, that is 0k0, k0k and 0k0, where k is greater than 0. If maximum energy eigenvalue of this h cap is 3 electron volt and corresponding to E equals to 2 electron volt, then the value of k rounded off to 3 decimal places in electron volt is, so we have to find the value of k for this matrix. So it is given that h cap equals to h naught cap plus h dash cap, where h naught cap equals to this matrix 3 cross 3 matrix, that is E00, 0E0 and 00E. Now the time independent perturbation h dash cap matrix is given by 0k0, k0k and 0k0, where k is greater than 0, that is given in the question. So total Hamiltonian is h naught cap plus h dash cap. So if we add these two matrix, then we will get this. So after adding those two matrices, we'll get the total Hamiltonian h cap equals to ek0, kek, 0ke, this 3 cross 3 matrix. Now this is a 3 cross 3 matrix, so if we want to find the eigenvalues for this matrix, we will get 3 different eigenvalues. So let the set of lambda be the eigenvalues of the total Hamiltonian h cap. So we know how to find the eigenvalues, so we will not discuss this in this question. We will directly go with the mathematical formulation for the to find the eigenvalues. So to find the eigenvalue, what we will do, we will take this determinant, that is E minus lambda k0, k E minus lambda k, 0 k E minus lambda, and this determinant is equals to 0. So to find the determinant, what we will do, we will just take this component and multiply it with this determinant 2 cross 2 determinant, that is E minus lambda k, k E minus lambda, and similarly for the other components also. So after doing that, what we will get, E minus lambda times E minus lambda whole square minus k square in the parenthesis minus k times this term in the parenthesis, that is k into E minus lambda minus 0, and that is equals to 0 here. So from the previous slide, what we obtained, that is E minus lambda times this term in the parenthesis, that is E minus lambda whole square minus k square times E minus lambda, that is equals to 0. So we can take E minus lambda common from this whole term. So we'll get E minus lambda times E minus lambda whole square minus k square, and again we'll get a minus k square. So that will give minus 2k square, and that is equals to 0. So from this equation, we can get either lambda equals to E, or this term, that is E minus lambda whole square minus 2k square equals to 0. So E minus lambda equals to plus minus root over 2k. So lambda equals to, that is E plus minus root over 2k. So we obtained 3 eigenvalues for the total Hamiltonian h cap. Those are lambda equals to E, E minus root 2k, and E plus root 2k. Now it is given in the question that our k value is always positive, that is greater than 0. The maximum energy eigenvalue of the total Hamiltonian h cap is
E plus root 2k that we have obtained from the eigenvalues of the total Hamiltonian, and that is equals to 3 electron volt, that is given in the question. Also given E equals to 2 electron volt. So, we will put this E value in this equation. So, what we will get? 2 plus root over 2k equals to 3. So, k value is 3 minus 2 divided by root 2 electron volt, that is 1 by root 2 electron volt. So, our k value is 0.707 electron volt, that is rounded off to 3 decimal places. So, this is the answer for the k value. So, we have solved this problem. So, what we did in this problem? We have just added these two matrices and we found the eigenvalue for the total Hamiltonian H cap. Then we equated the maximum eigenvalue with the 3 electron volt, and also we know the E value, that is the eigenvalue for the primary Hamiltonian H naught cap. By putting that in that equation, we found the K value for the perturbation matrix, and the K value rounded off to 3 decimal places in electron volt is 0.707. That is the answer for this question.
This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 2 marks, and the topic of the question is quantum mechanics. The question is, a hydrogen atom is in an orbital angular momentum state Lm, where m equals to L. If the angular momentum vector L lies on a cone which makes a half angle 30 degree with respect to the z axis, then the value of L is, so you have to find the value of L here. Let us see how to solve this problem. So for an orbital angular momentum state L and m, we have mod of Lz equals to mod of L vector times cos theta. So basically our L vector is making an angle theta with the z axis, and this component along the z axis will give the Lz. Now the eigenvalue of the Lz for this Lm state is mh cut, and the eigenvalue of the orbital angular momentum vector, that is L, is root over L into L plus 1 times h cut. So we will use these eigenvalues in this equation. So we will get mh cut equals to root over L into L plus 1 times h cut times cos theta. According to the question, it is given that the state is L comma m, where m equals to L. Again, the orbital angular momentum vector L lies on a cone which makes an angle 30 degree with respect to z axis. So we'll put m equals to L and theta equals to 30 degree in the previous equation. So we'll get L h cut equals to root over L into L plus 1 times h cut times cos 30 degree. So h cut and h cut will be cancelled out from both the side, and we'll get L equals to root over L into L plus 1 times cos 30 degree, that is root 3 by 2. Now we'll square both the side, so we'll get L square equals to this term root over L into L plus 1 times root 3 by 2 whole square. So L square equals to L square plus L times 3 by 4. Hence we will get 4L square equals to 3L square plus 3L, and from here we can get L equals to 3. So this is our answer. So according to our solution for this state L comma m, where m equals to L, the value of the L is 3, in which the angular momentum vector L lies on a cone which makes a 30 degree angle with respect to z axis.
This question was asked in the GATE Physics paper 2020. This is a numerical answer type question having 2 marks. The topic of the question is quantum statistics. The question is, consider a gas of hydrogen atoms in the atmosphere of the Sun where the temperature is 5800 Kelvin. If a sample from this atmosphere contains 6.023 times 10 to the power 23 of hydrogen atoms in the ground state, the number of hydrogen atoms in the first excited state is approximately 8 times 10 to the power n, where n is an integer. The value of n is, so basically we have to find the integer value of n in this 8 into 10 to the power n. One information is given here, that is Boltzmann's constant value is 8.617 times 10 to the power minus 5 electron volt per Kelvin. So now let us see how can we solve this problem. It is given in the question that a gas of hydrogen atoms in the atmosphere of the Sun where the temperature is T equals to 5800 Kelvin. Now we know the energy levels of the hydrogen atom is given by E with the subscript n equals to minus 13.6 divided by n square electron volt. Here n is the principal quantum number that takes the values 1, 2 and so on. Now the ground state energy of the hydrogen atom is given by E1 equals to minus 13.6 divided by 1 square. So here the principal quantum number value will be 1 and that will give minus 13.6 electron volt. And for the first excited state, the principal quantum number value n equals to 2. So the energy of the hydrogen atom in the first excited state is given by E2 equals to minus 13.6 divided by 2 square, that is minus 3.4 electron volt. According to the Maxwell-Boltzmann distribution, the number of classical particles in an energy level E at temperature T is proportional to n as a function of, that is number of the particles as a function of energy is proportional to e to the power minus e by kBt. Here kB is the Boltzmann constant. Let n1 and n2 be the number of hydrogen atoms in the ground state and the first excited state respectively. So n1 divided by n2 will give e to the power minus e1 divided by kBt whole divided by e to the power minus e2 divided by kBt. So this will give e to the power e2 minus e1 divided by kBt. Here it is given that n1 equals to 6.023 times 10 to the power 23, n2 equals to 8 into 10 to the power n. Here we have to find this n value, and temperature is 5800 Kelvin, and we have already from the calculation, that is E2, that is the energy of the first excited state is minus 3.4 electron volt. Energy of the ground state of the hydrogen atom is minus 13.6 electron volt. So E2 minus E1 is 10.2 electron volt. Now we will find the thermal energy value at the temperature T equals to 5800 Kelvin in electron volt. So kBt equals to 1.38 times 10 to the power minus 23, that is the value of Boltzmann constant, times 5800 Kelvin, and the unit of the energy will be joule here. To convert it into the electron volt, we have to divide it by the electronic charge, that is 1.6 times 10 to the power minus 19. So this kBt value in electron volt will be 0.50025 electron volt. Now we will use the equation coming from the Maxwell-Boltzmann distribution, that is n1 by n2 equals to e to the power minus e2 minus e1 divided by kBt. So we will put the values of n1, n2, e2 minus e1 and the kBt value. So n1 is 6.023 times 10 to the power 23,
divided by n2 value is 8 into 10 to the power n equals to e to the power 10.2, that is E2 minus E1, divided by kBT value in electron volt, that is 0.50025. So this will give 6.023 times 10 to the power 23 divided by 8 into 10 to the power n equals to e to the power 20.3898. Now the exponential part will give 7.16 times 10 to the power 8. From here we can write 10 to the power n equals to 6.023 times 10 to the power 23 divided by 8 into 7.16 times 10 to the power 8. So this will give approximately 10 to the power 14. So the n value will be 14 in the integer form. So we have discussed the solution for this problem and we found that the number of hydrogen atoms in the first excited state is approximately 8 times 10 to the power 14. So the n value in this question is 14.